Today we're going to talk about heat engines. Now we introduced them on Friday, but we didn't do any calculations with them. So the homework for tonight doesn't have any calculations with heat engines, which I'm sure is a major disappointment to you. But never fear. The homework that'll be due on Wednesday will have plenty of heat engine problems in it. So I've got first a page with a whole bunch of definitions. The first few you should know, or at least the first one you'll know. And then we'll work our way down, and I'll list them all here, and then I'll talk about them as we go through class. So first up there, we should have internal energy, PHYS, which is also known as the thermal energy, and it's the sum of the energies of the individual particles, their kinetic energy, their potential energy, not counting the energy of the entire group. So for instance, if you have a football and you want to say, what's the thermal energy or what's the internal energy, you wouldn't talk about the gravitational potential energy of the air in the ball. You wouldn't talk about the kinetic energy of the air in the ball, but you're talking about the kinetic energy of each molecule within the ball. So you're not talking about the motion of the entire ball, but the motion within the ball. Is that clear? Because it can be a little confusing. Okay, so we understand that. So basically, internal energy, you're only looking at the microscopic particles and not worrying about the macroscopic value. It's similar in nature, talking about rotational versus translational kinetic energy. Yeah.
Can you clarify something for me? If there's like a gas in a space, and the volume of the gas expands,
yes,
does internal energy go down or up? Or?
It goes down, and we'll talk about why later in the lecture.
Okay.
Okay, next one is heat. Heat is a transfer of thermal energy. Since it's a transfer, nothing can possess heat. And it's a transfer of energy that does not involve motion or work. Work is a transfer of energy that involves expansion or contraction. Going back to DJ's question, if I have a gas and the gas expands, then the gas did work on the environment. Because it did work on the environment, its internal energy has to go down because energy went out of it. That's the answer to your question. Then we have the heat engine, which was introduced on Friday. The heat engine is something that's designed to convert that thermal energy or internal energy into mechanical energy, to useful energy. And as I said in class on Friday, that it's impossible for a heat engine to be 100% efficient. You can never convert all of the energy that was thermal energy, motion and heat and whatnot, well, motion and heat, into heat. You can never convert it completely into mechanical energy. Now, I was asked a question this morning, is a water pump a heat engine? It doesn't run on thermal energy. It runs on electrical energy or some other form of mechanical energy. So right away, you can rule that out. The water pump is not a heat engine because it's running on the wrong thing. It's not running on thermal energy. Now, a heat pump is exactly the opposite of a heat engine. A heat engine, you put heat in and you get work out. But you also are always going to have waste energy that comes out. That's why it can't be 100% efficient. A heat pump, you put energy in it, and you move heat. So a water pump is a lot more like a heat pump because you're putting in electrical energy usually in a water pump. It could be mechanical energy. And then you're moving something. The only thing is instead of moving heat, you're moving water. So that's why a water pump is not technically a heat pump, it's a water pump. Then these are all, well, heat pump is new, and all of these down here will be new. So, going quickly, I looked this up to actually make sure for once I would pronounce it correctly, and it's isobaric. An isobaric process is a process where the pressure is constant. We often talk about the barometric pressure. That helps me to keep in mind what isobaric is. Barometer has to do with a barometer, the pressure. Isochoric processes is a process where the volume doesn't change. It's also called an isovolumetric, which if you said isovolumetric, it'd be simple. Iso, same, volumetric, volume. Isochoric means the same thing. It doesn't have a change in volume. It's constant volume. Then there's isothermal. Isothermal is constant temperature. Then there's adiabatic. And adiabatic is the one that people get the most confused about. Adiabatic means no heat. It's not iso because iso means constant. It's no heat. And finally, just to throw it in there, entropy, a measurement of how many ways a system can be obtained. How many people have heard that definition for entropy before? What definition have you heard for entropy before? The amount of disorder in a system. I choose to use a different, this is a more precise and accurate definition. The amount of disorder system is reasonably correct, but it leads to people misunderstanding what entropy means. So that's why I chose a different definition here. We'll learn more about it between today and Wednesday. So getting on to, I think this is the slide we ended with last class period. The one showing the heat engine. Remember, the first law of thermodynamics says that you cannot create or destroy energy. So you do have homework problems that says if you put this amount of energy in, and the total internal energy changes by this, how much energy goes out type of thing. Just balancing that. And we talked about very carefully for a heat engine to continue to run, you have to have the change in internal energy for a complete cycle is 0, which gave us the equations that I had written on here that balanced that said the net heat, which is the heat in minus heat out, is equal to the work out. So that's a nice, useful relationship. Now, the heat in, we often call Q sub H for the heat at high temperature. And the heat out, we often will call either Q sub C or Q sub L for the heat at a cool temperature or the heat at a low temperature. So oftentimes you'll see this instead of heat in minus heat out, you'll see something like that. But what that's saying is the energy for a complete cycle, the internal energy for a complete cycle has to stay unchanged. Now let's get into something new. First, just to make sure we're clear on the concept. Clear on the concept, did I? Okay. What is the purpose of a heat engine? Right? If we don't understand the purpose, we're going to have a lot of problems analyzing it. So which one of those is the correct answer? To convert mechanical energy into No. To convert heat into mechanical energy, yes. I didn't hear the last part. So to convert heat into mechanical energy. Now, to convert internal energy into mechanical energy, I wouldn't have argued against that probably, because you're taking internal energy, transforming it from one place to another in the form of heat. So I would probably be okay with saying convert internal energy into mechanical energy, but you could simply have a gas that you allow to expand and it does that, and that's not a heat engine. So it was D as in daddy, not father. So how do we get work? What's the equation that we learned for work a month or more ago? Okay, work is equal to force dot distance. I put it out there and I have vector signs because direction matters. If I have a force in this direction, but motion is in that direction, there's no work. So it has to be the same direction, so that's what the dot product means. Now, to understand how we're going to get work from heat, we'll consider a simple case of a piston. So we have a piston in a cylinder, and there's gas in the cylinder. So We'll just look at the pictures here on the right. They're efficient enough. If you have pressure in the gas, then it's going to put a force, and remember from one of our test questions actually, what direction is the force of that gas going to be on the piston? Always into it. So we're going to have a force in the direction shown by the arrow here that's equal to the pressure times the area of that piston. And if the piston is going to move, it's going to have the motion, well, it's written down below, but I can put delta x here, in that same direction. And so if I'm going to take the work, since the force and the motion are the same here, then force dot delta x is going to be force times delta x. Remember, dot was vectors, times is now taking the scalars, and I had to evaluate the direction in my head. And so if I take those together, the force is pressure times area. So the work is pressure times area times change in length. But for the cylinder, area times change in length is the change in volume for the cylinder. And so it turns out that the work is the pressure multiplied by the change in volume. And while this is, of course, a non-rigorous proof, it doesn't always, this calculation does not say that it's always true. It turns out that if you do it rigorously, it is always true. So the thermodynamic work is always given by pressure times change in volume. For those in calculus class, the work is integral of P dV. Notice what this is not. It is not change in pressure times volume. It is not change in pressure multiplied by a constant volume. It's a constant pressure multiplied by change in volume. That's an important thing to keep in mind. Now, if we look at our processes that I identified quickly, we had isobaric with constant pressure, isochoric with constant volume, isothermal with constant temperature, and adiabatic with heat is zero. Which of those four would tell me immediately what the work is? Immediately, no calculation necessary.
Isobaric.
Not isobaric. Isobaric, I would have to do some calculation. I know it's constant pressure, but I have to know the change in volume.
Isochoric.
Isochoric because
Zero.
because the change in volume is zero. Hence, the work is zero. So an isochoric process is a process that has no work by the definition of work. Now let's look at an isobaric process. So we have the cylinder again, and we are going to somehow miraculously keep the pressure constant. Why would we, I say miraculously keep it constant? What should normally happen if you compress a gas? Pressure should increase. So you're going to have to do something to keep the pressure constant. We're not worried at this point what that something is. We're just saying pressure is going to remain constant. So if the pressure remains constant, then it's easy to calculate the work. This is the one that DJ brought up. You have a constant pressure, so the work is pressure times change in volume. So you just take that constant pressure, multiply it by volume final minus volume initial. Now, it is important to think about units for a second here. What is the standard SI unit for pressure? Pascals, which is newtons per meter squared. What is the SI unit for volume? Meters cubed. And so if you're using those SI units, a Pascal times a meter cubed is going to be a newton per meter squared times meters cubed. Meters squared will cancel. I've left the meter on top, and it'll be joules, newton times meter. So if you're using the standard units, you'll get joules. But oftentimes we use other variables like pressure. What's another variable we might use for pressure? Torr. We rarely do in physics. In chemistry, you use it all the time probably, right? Because it's, at least traditionally, you would actually have mercury there and you just read it directly. So if you're using a different pressure measurement, be aware that you need to convert. Another volume measurement that we often use is liters or milliliters. And so if you're using milliliters, 1 milliliter is equal to 1 centimeter cubed. How's that going to relate to meters cubed? Multiply everything. Trying to change color here. Multiply everything by well, yeah, let's just multiply the right side. What am I thinking? So 1 milliliter is equal to 1 times 10 to the minus 6 meters cubed. Or thus, 1 liter is equal to 10 to the minus 3rd meters cubed. So you need to be a little fluid in converting units because you're going to have problems with different units. Now, what if you have a changing pressure situation? If you're in calculus class, 4 of you, what do? You integrate. But if you're not in calculus class, integration is not part of the process you have. So what you do is you do what they learn in calculus class when they're first learning what integrals are. An integral is done by taking, okay, my function is this tall, and if I take a little section, the area of that section is the little delta width times the height. And then the height changes a little, and I multiply by this little delta width, and you keep doing that, and you make a whole bunch of little rectangles. And you add up all the areas of those rectangles, and that's what an integral is. Okay, we're not in calculus class. So all we do is we say, if you were to do that process, you would have the area under this curve would be that integral, so the work is the area under the curve. That's the key output here. So I can look at my, my diagram here going from B to A, and I could say, what if instead of doing this process here, whatever it might have been, I start at B and I went like this and like this to get to A. I start at B, I end at A. I started and ended at the same starting and ending points. A state is only defined by its pressure, volume, temperature, and the number of molecules. For physics, we're assuming constant N. That's just assumed. If it's an ideal gas, PV equals nRT, so if you know the pressure and volume, you know the temperature. Hence, you're exactly the same state. Does that mean it's the same work regardless of how you got there? No. I had head shaking both ways. I'm going to go with DJ. He's my go-to man today. He's correct. No, it makes a difference because the green one here has a smaller area going from here to here, and then 0 area going here because the delta V was 0. What kind of process would I call this?
Isobaric.
That would be isobaric because it's constant pressure. What would I call this? Isochoric because it's constant volume. No work for that one. So there's less work for my isobaric plus isochoric than there is for the one that's shown. But if I start and end at the same place and there's less work, what do you think is going to have to be giving? You have the same change in internal energy but less work, so you have to have delta U is Q minus W. If W is smaller, what is Q going to have to be? In magnitude, yeah. Right, so we're going to have a balance there between these. So in a real problem, you would say, I start with this internal energy, I end with this internal energy. What happened in between? I really should do some with numbers. Actually, I want to stay here one more thing. By the definition of work in our textbook, remember some textbooks reverse this. The work is the work done by the system. That means it's energy going out of the system. It means that the force was the same direction as the motion. So what's happening to the volume of the gas if the force is the same direction as the motion? The force is always outward.
The gas moves outward.
Okay? The gas is going outward, gives you a positive work. So any expansion process is a positive work done by the system. Conversely, any contraction process is a negative work done by the system. So this here, going from bigger volume to a smaller volume, is that a positive or negative work?
That's a negative work.
It's a negative work because it was contracting. Delta V was smaller. Looking at a PV diagram, if your process is going towards smaller volume, going toward the left on the diagram, then it's a negative work. If it's going to the right, it's positive. So now we go here, and I have a complete cycle. Starts at A, goes to B, C, D, A. Well, actually, it shows two different methods, but the lower one's what I was talking about. Starts at A, goes to B, C, D, and back to A. Is that going to be the net work? When I do one complete cycle, is that a positive work done by the system, a negative work done by the system, or zero work done by the system? Zero seems like a logical answer, but it turns out it's not right. We start and end at the same situation, so we have to have the same internal energy. But the work is not zero. If you look at it going from A to B, you have more area underneath that than you have going from C to D. Is A to B a positive or negative work? Positive. C to D a positive or negative work? Negative. And of course, B to C, what can you tell me about the work going from B to C?
Since there's constant volume, then
Then zero. And likewise here. So we're going to have a net, work is greater than zero because it's a clockwise cycle, because the top was going to the right and the bottom was going to the left. Anytime it's clockwise, that'll be true. Clockwise cycles, you have a positive work. Counterclockwise cycles, you have a negative work. Now let's do some calculations. Let's not just look at theory, because when it comes to test time, you're actually going to do calculations. So here we have some numbers. We have a delta V given, and we have pressures given. I'm going to go one step further and say that V1 is 500 centimeters cubed, which makes V2 1,000 centimeters cubed. So I've put in numbers. I have the pressure and the volume that I start with. If I know the pressure and volume, what else do I know? Well, I don't know N and I don't know T. There's two things I don't know. So I actually cannot calculate without defining what an N is or what a T is. I kind of want to, so I'm just going to say we start at a temperature of temperature A equals 300. What unit should I use? Kelvins, thank you. There's no way I was going to use anything else, but I just want to make sure we're on that page. Because when you're using your calculations, always safest to use kelvins because you have to use it in things like the ideal gas law. So if I have Okay, so there I've converted into SI units for the volume. I have all of these. What's the first thing I would likely want to calculate just because I could? You guys aren't all into just because I can? I would typically say, if I'm writing a question for a test, I would say, how many molecules are there? Or how many moles of gas are there? Which would you prefer, molecules or moles? I'm specifying for monatomic ideal gas. So moles. There's PV over R. What is R? It's a constant. I didn't bring my phone. I can't look it up. It's 8.31 something. Somebody give me what R is? And there are different values of R. The one I quoted might be in the wrong units. You have to pay attention to those units. It's what?
I just saw it in GChem tutoring. It's like 1.902 times 10 to the something.
In units of?
Something.
Mira, help us out. You can flip your book open. It should be in the front cover of your book, I think.
Because there's a different one for liters.
Well, I put mine in meters cubed. So let's go for the one that's SI units. Pascals, meters cubed, kelvins, and moles.
Hold on.
Is it not there in the front cover?
Wait, maybe I have the wrong R.
Well, no, it's the right R. It's just we have to have the right units.
It's joules, joules/mole, right?
Yeah.
Okay, I have 8.314.
8.314. And those units were, you said, joules per mole Kelvin. Right, you do need to make sure you get the right units. The units, the number that Ryan quoted is a correct number. It's just in different units. So you just have to pay attention. Yeah. No. The units specify which one do you want to use. Right, so I wouldn't say use this one. You look at the units and that tells you which one you need to use. Or you could convert units and use another one. Right, you just have to pay attention to those units and use appropriate units. So what do I get for the number of moles here? I just made everything up, but just want to make sure we're going through some calculation here. Okay, so we got the number of moles. That's, of course, not actually the goal here. It's just a starting point. Now we go from A to B. How much work is involved going from A to B? I should have done this on another app where I have more room to write. Come on, there it is. How do I calculate work? It's the pressure times the change in volume. So that would be 1.5 times 10 to the 6th newtons per meter squared times 5.00 times 10 to the minus 4 meters cubed was the change in volume. Okay, that we can actually do in our head. Add the exponents. 6 plus minus 4 is 2. 1.5 times 5 is 7.5. So that's 7.5 times 10 to the 2, or 750 joules. So that's how much work was done. I don't have the heat yet. What do I need to know to get the heat? The change in internal energy. So if it's a monatomic ideal gas, I didn't give you an equation here. This is something that you need to put together from what we talked about in class on Friday, where we learned that the internal energy was equal to the number of degrees of freedom times, well, N times the number of degrees of freedom times RT, or capital N times the number of degrees of freedom, which is 1/2. You can't tell the difference in my R and my K in this writing. So if that's the case for monatomic ideal gas, the only degrees of freedom it has are the 3 for momentum. And so for monatomic ideal gas, it's going to be 3/2 NKT, or 3/2 lowercase n RT is the internal energy. So for this case here, I'm just going to have F equals 3. Therefore, U is equal to 3/2 nRT. And delta U, 3/2 nR delta T. Well, that's all good, except for one thing. I don't know what the change in temperature is. I can use the ideal gas law to calculate the change in temperature because I know the new pressure, well, same pressure. I know the new volume. And so I can go and I can calculate the new T. That's something you might be asked to do. Or I could say nRT is PV. So I could also say delta U is equal to 3/2 change in PV. That's going to work as well. Now this is pressure volume final minus pressure volume initial. That's different from work, although for a constant pressure case it's the same. So since this is constant pressure, it actually is the change in internal energy. Oh, come on. Just trying to make that look like an equal sign. Oh, that's the V that was printed there. It wasn't my handwriting. No wonder I couldn't erase it. So I'd have 3/2 the work in this case. So my change in internal energy is going up by 50% more than the work we just calculated. So 7.5 or 750 joules. Multiply that by 1.5, and that's the change in internal energy. So was heat added or taken out in this process? My work was positive, 750 joules, and my change in internal energy was 750 times 1.5, or my, yeah. So let me write this down. Work is equal to 750 joules. Delta U is equal to, what is 750 times 1.5? I am lazy today. Yes, that is correct. Using our first law of thermodynamics, delta U is equal to Q minus W. So Q is equal to delta U plus W. And so I'm going to have Q is equal to 1875 joules if I add those two together. I now have every possible calculation I can have for going from A to B. And you can repeat those calculations for every step going from B to C, C to D, D back to A. As a rule of thumb for these kinds of problems, I use a spreadsheet when I'm doing any of these problems. And in the spreadsheet, the first thing I do is I calculate the pressure, volume, and temperature at each stopping point. And then I calculate the work for the transition from one point to the next. And I calculate the internal energy, I forgot, at each point. So pressure, volume, temperature, and internal energy at each endpoint. And then I calculate the work between them, and then I can calculate the heat between them as well by using the first law of thermodynamics. Pretty complicated. That slide is very busy, isn't it? Fortunately, you'll have some homework where you can practice doing this. If you have questions with the homework, don't forget you can come talk to me, or you can email me, or you can come to our tutoring. Don't feel like you're stuck on your own, and if you don't figure it out, then all is lost. Next, isothermal and adiabatic processes. What did isothermal mean? Constant temperature. If it's an ideal gas, for ideal gas, then that means PV equals constant. If it's isothermal. So this line here, the isothermal, P is equal to some constant over V is that line. Now adiabatic, instead of constant temperature, it means no heat. So for the adiabatic line, you have no heat transfer, and it always is a lower work. Adiabatic is always lower work. I should put work adiabatic is lower. That's a W sub adiabatic for expansion. Have to be clear on that. Expansion is positive. If you start at point A and you expand isothermally versus adiabatically, the adiabatic one is going to end up with less work done. That is, it's a lower line. It follows a different relationship. Instead of PV is equal to constant, and so you end up with a lower line. These two equations here come from calculus. If you want to see how they're done, just come to class tomorrow. Otherwise, take it on faith that we can calculate the work for any isothermal process with the upper equation. It's, notice NKB, that's the same as lowercase n capital R, times temperature times the natural log of the final volume over initial volume. For adiabatic, it's the final volume, it's the change in pressure times volume divided by 1 minus gamma. And now you say, gamma? We haven't seen gamma. That's because gamma is equal to CP over CV. We've seen CV. Remember, we had a long discussion about CV on Friday. And what we determined was CV was equal to the number of degrees of freedom times 1/2 R. And it turns out that CP is CV plus R. And so it turns out this is the number of degrees of freedom times 1/2 R. I should use F instead of N. Plus R over number of degrees of freedom times 1/2 R. That's 1/2 R looks suspiciously like 1 over R. Those will cancel, and what you end up with is something that is easily calculable from the degrees of freedom. It's 1 plus 2 divided by degrees of freedom. Backing up the boat just a sec, degrees of freedom was the ways we could store energy. So for a monatomic ideal gas, you just had the three directions for momentum. If you had a diatomic, we talked about this in class on Friday. If it's at really low temperatures, you still just have 3. If you raise it up to around room temperature, you, for a diatomic, will introduce 2 rotational modes. For a triatomic, you would introduce 3 rotational modes. And then if you heat it up, for a diatomic, you'll introduce 2 more degrees of freedom for vibrational kinetic energy and potential energy. So for a diatomic, it could be 3, 5, or 7, depending on the temperature for the degrees of freedom. We'll look at that again maybe, but for now, just take on faith these equations so you can calculate the work for any of these standard types of processes. So let's do it real quick. Work for an isobaric process. What's the equation? Work is equal to isobaric. What does isobaric mean?
Constant pressure.
Constant pressure. If it's constant pressure, the work is, this is the first one we calculated, pressure times change in volume. Isochoric, what's the work?
0.
0. Boom. Isothermal, this upper equation. Isobaric, the lower equation. What do we call it if there's no heat? Adiabatic. Now this here is, oh come on, just open the video. There's at least a 1 in 10 chance it's opening the video. I knew I should have, there, okay, it's opening. And I think the sound will actually play too.
For you. October 2010.
Make it full screen. All I really want is to make it full screen. Is it so hard to ask? Oh, it's full screen. Now we just need to play again. All right.
A fighter jet roars across the sky. Suddenly, there's a burst of white surrounding the wings. The crowds watch in amazement. This isn't an engine malfunction, and the jet isn't about to explode. By slowing the footage down, this amazing vision becomes clear. As the plane approaches the speed of sound, it is momentarily engulfed by a blast of cloud. This is strange weather at its fastest. Meteorologist Steph Golter explains exactly how this bizarre cloud is formed.
To form a sonic boom cloud, you need 2 things really. You need a lot of moisture in the air, and you also need a plane travelling really, really fast. As the plane's hurtling along and getting faster and faster, the air ahead of the wing is all becoming really compressed, but behind it is all stretching out, and that allows the pressure here to drop. That allows the air to expand, and as it expands, it cools. And that cooling allows the water vapor to condense, and that's why the cloud forms.
It's the sudden change in pressure from high to low that creates this cloud formation. Steph demonstrates exactly how this pressure change works.
So we can imagine this to be our atmosphere then, and inside we've got some air and we've also got some moisture as well. Now we can pretend that this is our atmosphere around the plane, and we can show that going from high pressure to low pressure creates a sonic boom cloud. Now, I've only got 2 hands, so I'm going to need a little bit of help in order to make the pressure here a lot higher. Now this is what happens ahead of the wing. The air is all being compressed, but suddenly as the air passes over the wing, the high pressure goes to low pressure, and you've got a cloud.
Former Navy fighter pilot Pete Ross has witnessed the sonic boom cloud firsthand.
It's really the shock wave that's created by the winds that is going to create that conical vapor cloud. So somewhere aft of here, if you drew a circle around this airplane, including the wingspan, the big disc would be back here, and it may blank out the entire aft end of the airplane. It's just spectacular. I mean, it's a man-made phenomenon. There is nothing in nature. You never walk around and see a spontaneously induced shockwave cloud.
So it seems that even a plane can trigger strange weather events.
Enough of that. Okay, now that process of making the sweet, I think those things are really interesting to look at. That process, notice it was a rapid drop in pressure. It doesn't occur if you have a slow drop in pressure. Why do you think it occurs with a rapid but not a slow? I mean, this plays into today's lecture, obviously. It wasn't just for fun.
I think it's time for temperature to change.
It's actually the other way. It's giving time for it, but it's not temperature to change. And you're probably thinking about this exactly right, but the words get muddled in your head as far as what temperature is versus heat. Heat takes time to flow. And so if it occurs really fast, then the process will occur without enough time for any significant heat flow. So we call that an adiabatic process if it occurs really fast. So there's two ways to get an adiabatic process. One is to have perfect insulation, and one is to have a very fast process. So this process was very fast, so it's adiabatic. So if you have PV equals nRT, and the volume goes down, or excuse me, the pressure goes down, the temperature also then drops if the volume stays the same. If you do it quickly. If you do it slowly, something else can happen. And so that's adiabatic cooling. My experience with this, back when I was in college, I worked at a milk store, and we would take a soda and put it in the freezer on a hot day, because in Riverside, it's like 110 most every afternoon in the summer. And then you take that soda out of the freezer and you take the lid off, and insta-cloud, just like what she showed. Because you have high pressure in that soda can or bottle, and then when you release it, because it was cold already, it was close to the point of condensing. You suddenly cool it, the amount of moisture you can hold in cold air is far less than you can hold in hot air, and so it forms water droplets instantly. That's what was happening. They never said it again after the very beginning, but that whole thing with the airplane requires as a starting point very moist air at a reasonably high temperature so that you can cool it quickly. So if it wasn't moist air, it's not going to happen. How many people here are conspiracy theorists? Okay, we got a lot of you. It's fun. It's fun to read them. I think that it actually is good to read them with an open mind. You never know. You know, it could be the Illuminati is running our lives. Okay, but I have friends, educated friends, who believe that when they look up in the sky and they see a jet, they see a trail behind it. That's not a contrail. Contrails are what we just saw in essence. When you have a jet flying through fairly moist air, it will cause the rapid expansion after it passes through, and it will form a little cloud. That's called a contrail. So when you see the jet with the white trail behind it, it's this process. But they say, no. Actually, they're more like John Pinette, and they say, nay. They say that's a chemtrail because the evil governments of the world are trying to control the human population by releasing chemicals into the atmosphere that are surely poisoning us. So when you look up there at those contrails, you might believe it's a chemtrail. And it's actually really funny. If you look online, you'll find some real crackpot who got herself invited to some big thing where she spoke about this making no sense. But the political leaders there didn't know that. They're like, what? And maybe I shouldn't be so biased here. After all, I did say conspiracy theories are good. I will end here on the Clausius statement of the second law of thermodynamics. We've talked about the second law before. The Clausius statement is exactly the one I've said before. It's not the only statement. Next class period, we'll talk about another statement, that heat always flows spontaneously from hot to cold. The reason we end with that is because next class period, I'll talk about heat pumps, where we make heat do the opposite. We make it do what it doesn't want to do. Have a great day. I'll see you tomorrow for the lab final. That's the spirit.